Why is it so gosh darn satisfying to watch things blow up in slow motion? That is not the topic of today's video. Not at all. Today, I'd like to talk to you all about quantum tunneling. My name is the number 12, and this is Nerd Candy. Welcome to episode 1 out of at least 1 of Nerd Candy. Now, me and my Asperger's syndrome, we like to use way too many words to describe things. So this version is the short version of the video. I'll post the link to the full version on Blackboard if you would like to see it. And since this is the short version of the video, and it's being targeted at my fellow quantum mechanics classmates, let's go ahead and skip the introduction and walk on up to this little scenario. Here, the particle's energy is clearly less than the barrier, so what happens? It just gets rejected every time, right? You might be thinking of the model of classical physics. Classical physics has a particle do this. So yes, if we set it to the classical laws of physics, the particle will bounce off the barrier and its wave function becomes a reflected wave, equal to the initial wave but in the opposite direction. But it's called quantum tunneling, so it doesn't obey classical physics now, does it? This is where things... Hey, particle, where are you going? This is the good part! Man, and I've only got 6.3 quadrillion more where that came from too. But no matter, this is better understood with the wave function anyway. Once again, the first part of the wave is a basic sinusoid. The big difference comes when it reaches the barrier that starts at x equals 0. Most of the time, it gets reflected back with the same motion but in the opposite direction. But if it hits the barrier just right, the particle can penetrate the barrier by becoming a negative exponential, that is, a graph similar to e to the negative x. It loses energy but still manages to squeeze in. It's important to note that what you're seeing on the graph isn't the energy going down, it's the probability going down. As you might expect, the deeper into the barrier you go, the less likely it is the particle can survive. But if it does make it, what you get on the other side is a tiny sinusoid. And again, the size of it, or rather the amplitude, is not indicative of a lower energy, but how unlikely it is to make it there. And the fact is, it should be a lot smaller. Also take note that the wavelength is still the same as it was when we started. Now you're probably wondering how this can even happen at all. How can electrons just violate classical mechanics like that? Well, the simplest answer is Heisenberg's uncertainty principle. Because we cannot know the exact position and the exact momentum of a particle at any given time, the wave function is not really an exact definition of this is what particle is doing, this is what particle is. Another thing you might be wondering is, why should I care? What good does this do in the real world? And to that I say, what kind of hecking rock have you been living under? Come on, everybody knows about quantum tunneling. Just watch and learn. Hello, random bystander. Tell me, what is your favorite aspect of quantum tunneling?
What?
Quantum tunneling. What's your favorite aspect of quantum tunneling?
I don't know what quantum tunneling is.
What? What do you mean you don't know? It's quantum tunneling.
Quantum tunneling? Quantum of
Quantum
solace?
tunneling.
Like a tunnel for trains?
Quantum tunneling! Well, that didn't turn out the way I'd hoped. It did make me look like more of a psychopath than I really am in the real life, though. Just, by a slight margin. So that's something. Alright, all joking aside, let's take a look at why quantum tunneling really is important in the real world. This here is the tunneling diode invented by Ryoma Esaki, or as his friends called him, Leo, in 1957. It's usually made of semiconductor materials like gallium, germanium, or silicon. It can exploit quantum tunneling by treating the energy gap between the highest occupied ground level and the lowest unoccupied excited level as the barrier the electron should tunnel through. And while the odds of a single electron tunneling are usually 100 million to 1 or worse, remember that electrons are tiny. Tunnel diodes contain quadrillions of electrons. So while that graph I showed simplified how it could happen to one electron, in reality the scene looks more like... And so, because of all that action, we still get billions of electrons to make the tunnel every second. If the electrons are going forward, they flow as a PN diode until you increase the voltage. By increasing the voltage, you increase the tunneling distance, and so the current stops because the tunneling probability gets so low. So this is a way you can get an adjustable current to flow. If the electrons go backward, it converts AC, alternating current, into DC, direct current, which only flows in one direction, so we'll know exactly where the electrons are traveling. So both things help us control an electric device.
However, due to the disappointingly low power level, they are not widely used in many appliances.
Tunnel diodes are very resistant to radiation, which is why a lot of space probes use them to control current in the harsh environment of being unprotected from solar wind. Tunnel diodes are also notable for their extremely good longevity. In fact, some of the diodes Esaki himself built back in the early 1960s are still up and running in 2018. And if electrical appliances aren't your thing, quantum tunneling occurs in nature inside of stars. You know how nuclear fusion requires protons to stick together to form a bigger nucleus, even though they're both positively charged and don't want to touch each other? Well, the strong nuclear force performs quantum tunneling to get the proton through that energy barrier in order to stick to the other proton to become a helium nucleus. And that's how stars contain so much energy in them. Quantum tunneling also works in the reverse way, in radioactive decay. In this case, the particles break away from the atom structure by tunneling backward through that potential barrier. And of course, this leads to the energy being split apart as well. This is important for development of life on planets, because radioactive decay, the release of particles and energy outward, can provide an energy source for neighboring planets. If the source is relatively constant over a large period of time, like with our Sun, then there will be a wider habitable zone for a planet to reside in that may achieve life. Well, that wraps up episode 1 of Nerd Candy. Hope you enjoyed, and, naturally, with this being my first time doing this, I have no idea how to end this video. Here's my cat, Sparky, doing cat things. Sleeping. That's the most cat thing of all. Other cat things. He doesn't like his water bowl anymore. Sparky like the camera? Sparky likes the camera?
That's what they're gonna name
Huh?
the old sports
Sparky.
stadium down here.
Hey, Spark.
They used to have the circus, which
Sunky.
exists, and other things.
I'd rather check out the billiards.